Let's talk about dimensionality reduction for a few minutes. Here's an outline of this brief discussion about dimensionality reduction. First of all, I'll cover what is meant by dimensionality of the data. I'll talk about the curse of dimensionality, why high dimensionality is a problem, and why we need to reduce the dimensions of the data. And finally, talk to you for a few minutes about the approaches of dimensionality reduction, or the techniques that you can use to reduce the dimensions in your data. The overall dimensionality of the data refers to the overall number of attributes, fields, variables, or features within the data. So I use all these terms to describe essentially the same thing. They are basically just the columns of the data that you have. If you said, what is the dimensionality of the data? We have a few different techniques in our programming languages to get that for you. In Python, you can use shape, and in R, you can use str for the structure of the data. So the bottom line is, however many fields or columns that there are in the data, that's your dimensionality. For example, I talk a lot about the college scorecard data. That has well over 500 dimensions, 500 columns. I think it might be more upwards of 1,000, some of which are deprecated or not really used, or just sliced and diced in a bunch of different ways. The college scorecard data is considered a high dimensional data set. The curse of dimensionality refers to this increasing difficulty of analyzing data that has a high number of dimensions. So as the number of attributes or dimensions increase, so doesn't the complexity of the analysis. There are other reasons about why we should be concerned about the dimensionality of the data, which I'll talk about next. Why is this a problem? Imagine you're trying for a minute in Excel, trying to optimize a solution where there are over 1,000 variables or 1,000 different buttons you could push. Your PC would probably crash if you're trying to use that solver in Excel. Or even in Python or R on your own machine. Let's say you have 16 gigs of RAM on your own machine. Your machine might start to hang or slow down or run out of RAM. Entirely possible. Okay? So there are potential issues with high dimensionality. If we have more features than observations, we can run the risk of overfitting our model, especially in classification tasks. Also, observations have a harder time clustering and converging into clusters because there are too many dimensions. And this fact causes every observation to appear pretty much equidistant from all the others. And the reason I say that is because in clustering, we use Euclidean distance to quantify these observations. So using Euclidean distance starts to cause this problem. And we don't want distances to be equal because the cluster analysis won't show anything meaningful or useful. So that's another reason why we have to reduce the dimensions of our data, and again, especially in clustering tasks and unsupervised learning tasks. Why should we reduce the dimensions? Because a very large number of inputs or dimensions will lead to poor performance of machine learning algorithms. And a larger number of dimensions means that the volume of data is very large, which also means that there may be data that's non-representative, or the data contains noise. We want to eliminate noise. Furthermore, we simply want the essence and meaning of the data projected onto relatively few dimensions, or as few dimensions as we can get. And finally, it's also much easier to visualize data in two-dimensional space, XY axis, rather than 100 dimensions. Here are some of the approaches used in dimensionality reduction. In this course, I focus on using PCA, which is a matrix factorization method. But there's several different methods we can use. We have feature selection methods. Then we have techniques from linear algebra called matrix factorization. And principal component analysis, or PCA, is one of those matrix factorization techniques that we can use to reduce the dimensionality of our data. As a matter of fact, PCA is one of the most commonly used dimensionality reduction techniques that we have available to us. There's also a set of techniques called manifold learning. I won't be covering that in this class, but some of those methods include SOM, Salmon's mapping, MDS, which is multidimensional scaling, and T-SNE. We also have autoencoders, so you can use things like deep autoencoders that are all built on deep neural networks. One example being LSTM autoencoders, which are long short-term memory autoencoders. So that is outside the scope of this class, but let's take some time to focus on PCA, which is, again, one of the most common techniques that's out there, and it's a good place to start. All right, thank you so much. Please go ahead and continue the learning and let us know if you have any questions.